So this is the second installment of the evolution of populations. So I thought we both might need a break there. Where we left off was just talking about the fact that the amount of genetic variation that we see cannot possibly be explained by mutation alone. So this brings us to trying to figure out, how do allele frequencies change in populations then? Remember that genotype dictates phenotype, which means that if you have a change in your phenotype, there's got to be some change in the allele frequencies. But remember that during Darwin's time, the genetic basis for variation within populations wasn't even understood yet. We didn't know about meiosis, we didn't know about how gametes were formed, etc. In fact, scientists believe that selection should always favor an optimal form, which would really just get rid of variation to begin with. And in fact, blending inheritance was still accepted. So how did variation exist? Well, in comes the Hardy-Weinberg principle. Now, this is after we learned about some genetics. Hardy was an English mathematician and Weinberg a German physician, and they basically determined the requirements of a static population. So this is very important, the static population. What that means is this is a population that's not changing. Because if you know about a population that's not changing, then you can observe some of these factors that are not true and talk about a population that might in fact be evolving. So what we'll take a look at here are the 5 requirements for a population to be in equilibrium. And in short, these are the 5 requirements. So a population must be large, no genetic drift, which we'll talk about. There must be random mating. You may not select your mate. Anyone will do. Scary. There must be no mutation and no migration, which would, of course, introduce new genes, so no gene flow. And there must be no natural selection. Now, if all if all of these conditions are met, then no genotypic changes will occur in a population from generation to generation. Thus, proportions will go unchanged, and a population would in fact be in Hardy-Weinberg equilibrium. But of course, this doesn't really work because sometimes at least a few of these things are occurring, especially migration. And mutation you can't exactly control. So what we're going to do now, and this is where you really need to start paying attention, hopefully you have been anyway, and take a look at how they developed their theory and how to use this equation. We're going to go through a couple of real basic uses of it, but later in class we'll be doing some actual problems. So it's important that you understand the derivation of this. In math, I wasn't really into the derivation of an equation, but this one is very important actually. So I'm going to walk you through that. So I'm going to highlight this so we can remember what we are referring to. If we had 2 heterozygous individuals of some generic trait, and we used a Punnett square to cross them, if you can just pay attention to the bold at first, that should all make sense to you. But if we really want to study the alleles separately, we need to assign them a different letter. So we'll call the dominant allele P and the recessive allele Q. And so when you do your Punnett square or multiply them like you might have done in more basic math, you'll see that P times P is P squared, P times Q is PQ, etc. PQ and then Q squared. So you see you have 2 PQs, okay? So the equation is right here, and this you need to know. Here, P plus Q squared, this is your allele frequency, and it's squared because of the fact that you're using it twice over here. These represent your allele frequencies. P is your dominant allele frequency. Q is your recessive allele frequency. Then, if you were to take your results, P squared is your homozygous dominant individual. 2PQ is your heterozygous individual. And then Q squared is the homozygous recessive individual. These represent the genotype frequencies. So you could think about this side as representing your gametes, and this side is representing your offspring or zygotes. So going down a little bit further, just defines what I said in with my voice above. P equals the frequency of the dominant A allele. Q is the frequency of the recessive A allele. Therefore, P plus Q must equal, nope, that should be a plus. P plus Q should equal 1. With the reference to the genotypic frequencies of the zygote, P squared is the frequency of your homozygous dominant genotype, 2PQ, the frequency of the heterozygous genotype, and then Q squared, the frequency of the homozygous recessive genotype. But let's pay attention to this. If we want to know the frequency of alleles in a population, not phenotypes, but alleles, you can't just pay attention to your homozygous dominant or your homozygous recessive individuals. Remember that those heterozygous individuals carry half of the the dominant A allele and the recessive A allele. So we really do have to pay attention to those as well. So let's look at an example. The book that I got this picture from uses this example with some cats. Let's say that there were 100 cats, 84 black, 16 white, and you wanted to get at the allele frequencies of that population and how many were heterozygous versus homozygous dominant. And of course, we'll assume that dominant is black, just general inheritance patterns, no incomplete dominance or anything of that nature. So our cats that have the black phenotype would either have homozygous dominant genotype or heterozygous genotype, and of course the white would be homozygous recessive. The first step that you want to do to use your Hardy-Weinberg equilibrium equation is to find your allele frequency. Now we know the white genotype since white is recessive. So that one's easy. 16 out of 100 is 0.16. Therefore, 0.16 is the homozygous recessive genotype frequency as well. Therefore, Q squared equals 0.16. Let me go back up and show you. Q squared, remember, is the homozygous recessive. So if Q squared is 0.16, then all we need to do is take the square root of it to find the allele frequency. So we take the square root of Q squared or square root of 0.16. Then what we have is 0.4 is the B allele frequency. So now we know B, and we have 1. All we have to do is plug them in. So if P plus Q equals 1, then P plus 0.4 equals 1. And then we just use one allele frequency to find the other one. We already found the Q frequency. Now we want the P frequency. So this gives us 0.6. Hopefully that made some sense. Once we found the allele frequencies, we can then find the genotype frequencies. In other words, what proportion of our population are homozygous dominant? What proportion are homozygous recessive? So next step, find the genotype frequencies. So remember how we found the homozygous recessive genotype frequency was 0.16. Now we want to figure out the homozygous dominant and the heterozygous. Remember that homozygous dominant will be P squared, heterozygotes will be 2PQ. If we take our P squared, which was 0.6, and we actually square it, instead of doing the square root, right? Because now we're finding the genotype frequency, not the allele frequency. Go back and reference your equation so you can keep everything straight. Is 0.36. That's our homozygous dominant genotype frequency. So all we have left to find is 2PQ. Well, we just plug it in. 2 times P times Q, which is 0.4 and 0.6, then you get 0.48. And this all better add up to 1. 0.36, 0.48, 0.16, and they all add up to 1. Now, here's the problem though. Let's remember that not all populations are in Hardy-Weinberg equilibrium. Let's say, for example, that the homozygous dominant and homozygous recessive frequencies were 0.45 and the heterozygote was 0.1. Why would that happen? Why would they have such a low frequency? Perhaps the heterozygotes don't live as long, or maybe individuals choose to mate with genetically or phenotypically similar individuals, which is actually pretty common. What would happen is if these guys always mated and these guys always mated, then they would have the same genotypes in their offspring. And if two heterozygotes mated, remember that half of their offspring actually create homozygous individuals. So you create quite a bit of homozygosity in that case. But getting back to Hardy-Weinberg, remember, it's just a null hypothesis. It's a control. We know it's never going to be true. Populations are always going to be changing because they're always going to be breaking these 5 rules, or at least 1 or 2 of them. So populations not in equilibrium indicate that at least one type of evolutionary force is in action. And this is usually the case. So what are those? And why do allele frequencies change? Allele frequencies, and therefore genotype frequencies, do change in natural populations. Hardy-Weinberg is just a baseline to measure up against. Many factors can change allele frequencies, but only 5 really do it significantly. And of these 5, there are only 3 that have the largest impact. Mutations, of course, these are the ultimate source of variation. And what that means is it's the most basic or fundamental source of variation. Individual mutations occur so rarely that mutation alone usually doesn't change allele frequency very much at all. Now, gene flow, this is a big one. I'm going to highlight it. I want you to highlight the 3 main ones. Gene flow is a really important source of genetic variation. Populations here would exchange members or even gametes, and you might ask, well, how could you exchange a member? I could see that, immigration, emigration, but how do you only exchange gametes? Remember about pollen, and pollen flies through the air, and that's simply plant sperm, so that's one way to do that. Non-random mating, what this has to do with is you selecting your mate, basically. Sometimes this actually results in a little bit of inbreeding. It depends on the population structure. But what's important is it changes the proportion of heterozygotes that make up the population. The 4th way that we get allele frequency, and the second one that's really important, is genetic drift. This is random changes in allele frequencies, which is really common in small populations. We'll talk about population bottleneck and the founder effect. These are really just statistical accidents where you get these random fluctuations in the frequencies of alleles, and it can cause population sizes to drastically decrease, and so your new founding population is perhaps different than the previous one. And then last is selection, and what this is really talking about is the different forms of natural selection. This will produce adaptive evolutionary change because it depends on the nature of the environment, and it's the only one of these 5 that produces adaptive evolutionary changes. So the Hardy-Weinberg principle states that in a large population, mating at random and in the absence of other forces that would change the proportions of the different alleles at a given locus, the process of sexual reproduction alone will not change its proportions. There are other factors involved. And here again is our equation, just reminding you of what they mean. So what we'll do next is we'll review these 5 agents of evolutionary change that are basically breaking the rules of Hardy-Weinberg, but I think we should all take a short break first.